Hey folks, Todd Coburn here with the Aerospace Structures series. This lecture is continuing our study of composites. Today we're going to focus on hydrothermal analysis of composites. What this means is, while last time we learned about classical lamination theory, how to evaluate the stresses and strains on a composite laminate, today we're going to look at how do we evaluate temperature changes on the composite, how do we evaluate moisture changes, and how do we couple those effects with our external loads. So stay tuned and let's see how it works. All right, let's start by recalling what we've learned about thermal stresses and strains for isotropic materials. Imagine an isotropic rod subjected to a change in temperature. That change in temperature is going to introduce strains in the element given by alpha delta T, where alpha is the coefficient of thermal expansion and delta T is the temperature change. And if we multiply that strain, that thermal strain, by the original length, we'll find out how much it deflects. If we multiply by the original thickness or width, we'll find out how those dimensions grow as well or contract. We can write the strain as alpha delta T. We can also write it as the ratio of the deflection divided by the original length. So these principles of strain and deflection are critical to understand. Remember, alpha is our coefficient of thermal expansion. We also want to recall that the stresses associated with a thermal strain are, there's no stress associated with a thermal strain. We can denote the thermal strain when we have an unrestrained isotropic rod. Remember, we have no stress. We can call that strain the free strain and denote it as epsilon F, since that is the amount that it strains due to the freedom of movement and due to the idea that that strain is stress-free. The stress that would have been induced would have been represented by Hooke's law, but since it is free to expand, it does that expansion with no stress, just like sitting in the tub when you're absorbing moisture and you get bigger and bigger and bigger due to the moisture coming into your body, but you're stress-free. But if the tub is too small and you start pressing against the sides of the tub as you expand, that's going to introduce some stress. Materials are people too, and if those thermal deflections and strains are constrained, we're going to get stress, but if they're not constrained, there's going to be no stress. Now, if that isotropic rod is constrained, though, it develops stress, and the stress is developed in proportion to the amount of constraint. So if that rod is completely constrained such that it can't get longer, then it will develop stress in accordance with the total strain restricted. So we could take that thermal strain that it wanted to do, alpha delta T, and that amount of strain being inhibited will cause a stress according to Hooke's law, as we see here. If we had external loads on this rod, it would have strained as well, according to Hooke's law, and the total strain on the element would be whatever it strains due to temperature effects plus whatever it strains due to loading effects, as we see here. And so we can write it this way. Now we could actually write the stress. Now remember, the thermal strain, we're talking about an unrestrained rod subjected to temperature change, and the total strain minus the amount of strain caused by the temperature change is the amount of strain left to cause stress according to Hooke's law, as we see here. Now this lowermost equation, where we're taking the total strain in the element, reducing or removing the amount of strain due to the temperature change, and applying Hooke's law to this to calculate the stress in the element, due to that combined effect. This idea is the key to understanding what we're going to do with composites. So let's go ahead and take this a step further and look at how it behaves for a composite. Now remember, that was for isotropic materials, given these two equations for stress and strain. And for laminates subjected, if we have a lamina subjected to a temperature change, we can expect similar behavior, but now we have a lot more coefficients. Instead of just an E, we have a whole matrix of values that we need to account for. And this is how we might do that. Okay, now if we focus on a single orthotropic lamina, one layer, it happens to be orthotropic, and we apply what we've learned about thermal strains, then we can write it this way, where the stress in material principal directions is equal to that strain, which is the strain in the material principal directions, minus whatever we find, the total strain, minus the strains due to thermal effects, all that pre-multiplied by the Q matrix. Now this is if those loads and we're focused on the thermal effects in the principal material directions. If we happen to want to evaluate this in non-principal directions, then we can write it this way, and we can actually do this on a layer by layer level, where we take the strains on the layer in body coordinates minus the thermal strains for that laminate, pre-multiplied by the Q-bar matrix of that ply to get the stresses in the ply. This is the key to this analysis, and this is how we can take total measured strains, remove the thermal part of it, pre-multiplied by the Q-bar matrix, and get the stresses in the ply in body coordinates. Now stay tuned, because this is the key to how we're going to do this analysis, or actually it's one key or one building block for our approach. So let's go ahead and take a look at, take this further. Now this was our relationship for a single ply. A single ply, total strain, subtract out the thermal strain, re-multiply by the Q-bar, and that gives us the stresses in that ply in body coordinates. Now, if we want to, we can write this, we can multiply this out and write it this way, where the Q-bar matrix times the strains in the element minus the Q-bar matrix times the thermal strain, the alpha delta T part. Okay? Now, if we denote this part, this thermal part, as with a superscript T to show that it's for thermal alone, so we're focusing only on the thermal part of this, then we can write the stress for the thermal part this way. All right? Now recall, just like we saw with classical lamination theory, the running load in the ply is just the stress in the ply times the integral across the thickness, and that stress times that change in thickness gives us the running load in that ply. We can write that in this manner, where we take the Q-bar of every matrix, multiply by the alpha delta T, multiply by the Z minus Z minus 1. Remember, Z is at the bottom and the Z minus 1 is just above, which is actually just the thickness. So the Q-bar times the alphas times the thickness gives us what each ply contributes to the running load. So if we had a certain strain, that strain would be caused by these running loads in that ply. These N sub T, N xt, N yt, and N xyt, these are all what we're going to call fictitious thermal loads, running loads, because these are the running loads that would cause the same exact strains. Remember, what we're doing here is taking the Q-bar and multiplying by the thermal strain alpha delta T. That alpha delta T thermal strain is how that ply wants to behave in response to the temperature change. And so when we multiply that, if we just think of that as just a strain, we pre-multiply by the Q bar and by the thickness, that's going to tell us how much running load is caused by that thermal strain, or actually how much running load would cause the exact same amount of strain as the thermal strain. This has the idea then, this n to the superscript T then, and when I say n, I'm talking about all three values, right? We have one in the x direction, one in the y direction, and a shear direction. We're getting all of that since we're using all of the alpha delta T's. Remember, that Q bar times the alpha delta T, that is a stress, and we multiply by that Z minus 1, which is just a thickness, we're getting the running load. And since we're dealing with a thermal strain, that thermal strain, and we're turning that into a stress, but those thermal strains don't induce stress, but what that means is these are the running loads that would cause the exact same amount of strain. And this is how we're going to count for that thermal strain, is by figuring out the virtual or imaginary loading that would cause the exact same effect. This doesn't mean that lamina experiences stress due to that strain. It means this mechanism of turning into the imaginary force that would have the same effect will give us a tool to evaluate how the whole laminate responds. Okay? So these thermal loading that we calculate like this are imaginary, virtual, fictitious values that result in the same strain as the temperature change did. This is a key and critical principle and idea to support our methodology. Regardless, looking at this further, this means we're taking the topmost ply, we're taking its Q bar, multiplying by its alphas and the delta T on the whole laminate and its thickness. And then we're doing the same calculation for the second ply, same calculation for the third ply, same calculation for the fourth ply. Imagine a series of transparencies. Remember, we used to, a couple decades ago, instead of using PowerPoint and all these other electronic tools to communicate teaching, people were using slides. They're clear, see-through sheets of material that you can show students what you're talking about. And if you imagine that each of these multiplications are occurring on one of these see-through plies, and then you shove them all together or add them all together, we're getting all the effects. So we're doing this calculation for each and every ply and then just summing them up. And that gives us the total running load on the laminate. We're getting the running load, the virtual running load on each and every ply, and when we add them together, we're getting the total running load on the composite laminate. Now we can do the same thing for the moments, because our moments under classical lamination theory were calculated like this. All we need to do now is take the stress times the dz, which is just the thickness, which gives us a, and then take that and multiply that by the z position, and that is going to, stress times the z times the dz is just a force times the z position is giving us that moment. So this allows us to calculate the moments. So our virtual moments due to thermal, or the imaginary moments that would cause the same exact thermal strains, can be evaluated by taking the alpha delta t's pre-multiplied by the Q bar, all of that over 2 multiplied by the z squared minus z minus 1 squared parameter, which can be written like this, right? So as we saw before. So this gives us the total imaginary running loads and moments that would result in the same thermal strains. Got it? All right. Now, if we had not had a change in temperature, if we had external loads, we saw these relations for external load, right? We had the ABBD matrix, which was multiplied against the midplane strains, and curvatures. So this is for external load. And if we wanted to account for external load and temperature, what we would have to do is the running loads due to external loads minus the imaginary running loads that cause the thermal strains. While this external load thing tells us how to relate strains and curvatures to running loads and moments, if we want to account for temperature changes, we need to remove the part that was caused by this thermal strain, because the thermal strain induces no stress. And a clever and convenient way to do that numerically is to subtract out these virtual or imaginary running loads and moments from the running loads and moments of the lamina. So once again, where before we were looking at loads versus strains and curvatures, now we're saying is, hey, we've got a set of running loads of, we've got a set of strains and curvatures. And these are caused by external loads and they're caused by thermal loads. So in order to figure out how much running load actually causes stress, we're going to take that part that causes take that strain, the ABBD matrix times the strains and curvatures minus the running loads and moments that would give the same effect as the thermal temperature change does. And that is going to be our approach. This is how we can do this. Now, stand by because we're going to look at this a bit further. Before we do that, we're going to look at the same kind of idea for hygroscopic loads. Now, this word hygroscopic has the idea of moisture. We talked about thermal loads if we get a temperature change. And now we're going to talk about what happens if we have a moisture change. Now, the idea of thermal load is one that's familiar to us because it's covered in the elementary chapters of our undergraduate structural strength of materials courses, structural mechanics courses, mechanics of materials courses, and stress analysis courses. The reason we didn't deal with hygroscopic or moisture-related effects before is that most of the isotropic metals that we deal with they don't absorb moisture. Hence, it's a non-issue. But when we start talking about organic materials, many of the composites we're going to deal with are made of organic materials that do absorb moisture, and this can actually be a significant effect, not only affecting the strength, but also affecting the behavior. So now we're going to introduce a method for calculating moisture effects, which we use the word hygroscopic for that. We can actually simulate the behavior of an isotropic material to hygroscopic loads in the same manner that we did for thermal loads. What that means is our strain due to moisture can be thought of, instead of alpha delta T, it's beta delta C, where this beta is the coefficient of moisture expansion. So if we multiply that by the change in moisture concentration. So what's a moisture concentration? Well, with metals that basically they have no moisture absorption, our beta is 0, and therefore it's never going to change the concentration because the concentration of moisture is 0. If we talk about foams, like a Roacell foam, like the kind of stuff we used on the Delta program, this stuff can absorb 10, 13, or more % moisture. That means if we go from dry foam when it's manufactured to being saturated in use of like 13%, that means the change in moisture content, the delta C, we're going to use a C for this as the variable for this moisture concentration, would be written as 0.13. If it's 13% moisture, it'd be 0.13. If we're talking a graphite epoxy face sheet, commonly these might be a saturation moisture content of maybe 1% or 1.2%. That means the delta C going from manufacture when it's dry to fully wet, if it gets in a really wet environment, would be 0.1 or 0.12. 0.01 or 0.012. 1% would be 0.01. 1.2% would be 0.012. You got that? So that's how we get the moisture concentration. How do you get that in real life? Well, you can take that material, let's say you grab a sample off of a rocket or whatever you're building. You can cut that loose, weigh that sample, put it in an oven and dry it and reweigh it, and that change in weight, assuming you don't burn off any of the actual material, will be the moisture concentration. And you can write that as a decimal, and now you got the moisture content, the change in moisture concentration. So the strain is beta delta C. The deflection, it deforms in the same manner that materials do under thermal loads. It's going to be beta delta C times L, just like this, written in the same manner. The strain, therefore, once again, we can write it a different way as the deflection divided by the original length, and we can write it like this. Once again, when we have moisture, that's going to, the strains due to moisture are also going to be stress-free, and we can denote those as the free strains, epsilon subscript F, for the idea that there's no stress associated with that unless there's constraining action. Okay? As we saw before, we can constrain, if we completely constrain the rod, then that will introduce stresses. However, if we have an unconstrained rod, there's no stress. Now, if we have a isotropic material that experiences both external load and moisture effects, we can write the total strain like this: the strain due to the moisture, the external load, plus the strain due to hydrothermal effects. That total strain is written this way. If we want to calculate how much stress is there in the element or the structural member, we have to subtract the moisture part of that strain from the total strain, just like we did for thermal loads. So hold these ideas and let's go to the next slide. Once again, we saw for isotropic material these two relations for strain and for stress for an unconstrained rod, which for laminate materials or composite materials, we might have relationships like this. If we have an orthotropic lamina subjected to these, we can write it this way in principal directions, just like we saw for thermal. And our stresses in each ply or each lamina can be written this way, as the Q bar times the total strain minus the strain due to the moisture effect. Just like we saw for thermal, the only difference is now we have a beta delta C instead of an alpha delta T. You got that idea? All right. We're then going to develop how a laminate responds in the same manner. We had this relationship for a lamina, which we can write like this. And if we denote our moisture stress with the subscript, or the superscript H for hygroscopic, then we can write our stress in a single lamina with this relation. It's the Q bar times the beta delta C. Now, once again, our running load, it can be calculated by integrating the stress across the thickness, and the running moment can be developed by integrating the stress times the Z position, the Z bar, times the change in thickness, which means we can write this in this manner. This gives us the virtual or imaginary running loads and moments that would introduce the same exact strains as our moisture effects. Once again, we saw this relationship before we started dealing with this. And if we go and start measuring the actual strains, take this total strain and curvature that we find on an element, and if we want to calculate how much of that causes stress, we would actually have to remove the part of the fictitious virtual running loads and moments due to moisture or hygroscopic effects from that strain, from the running loads of the element. Okay? So we have seen this approach for thermal loads, and now we've seen how this works for moisture effects. We're now ready to combine these effects. So if we want to evaluate a composite laminate for external load coupled with moisture coupled with thermal effects, we can write the total relationship like this. The running loads and moments on the element are going to be equal to that ABBD matrix times the midplane strains and curvatures. Now these strains and curvatures, once again, are the midplane values, and they're whatever we measure, which includes whatever the load contributes. It includes whatever the temperature contributes. It includes whatever the moisture concentration contributes. So in order to get the portion of that for evaluating stresses, we're going to need to subtract the moisture and thermal effects, which means we're going to subtract those virtual thermal loads and the virtual hygroscopic loads. We can write it like this in expanded notation, or like you see to the right in condensed notation, where the N and the M each represent the three values of running load and moment. The ABBD matrix represents each of those matrices has 9 inputs. We have our midplane strains, 3 values, and curvatures, 3 values. We subtract out 3 values of thermal fictitious running load and 3 values of thermal fictitious running moment, and we subtract out the running loads and moments for the hygroscopic effects as well. Now another way to write this is to bring these fictitious loads due to thermal and moisture effects and bring them off to the left side of the equal sign. And we can introduce a new variable called the N bar or M bar, which is our augmented running loads and moments, which have the effect of everything. And that means we're going to take the total running load and moment plus the part due to the thermal plus the part that represents the hygroscopic, and that is equal to the ABBD matrix times our midplane strains and curvatures, which we can write in condensed notation like this. This is the backbone of classical lamination theory for evaluating hydrothermal effects. Now we're going to actually use this if any of these, like let's say there's no moisture change, then our N bar is a little different. If say there's no moisture change, then our N bar and M bar are a little different. Let's say there's no external loads, then our N bar and M bar are a little different. But we can use this relation to evaluate any of those cases. Let's drill that down even further. So let's start by saying, okay, let's say we have external load and temperature changes and moisture concentration changes. Actually, first, we're going to focus on just delta T and delta C, thermal and moisture change. And then on the next slide, we'll bring in the external load part too. So if this is true, we've got a temperature change and we've got a moisture change, okay? We're going to compute our global expansion coefficients for each ply. What we have to do is go and find the principal material thermal coefficients and the principal material direction moisture coefficients for each and every ply. We can use these with the transformation, apply the transformation matrix to each of these in order to turn those into body coordinate values for each and every ply. That means if we have a 5-ply laminate, we're going to have 5 sets of values for thermal and 5 sets of values for moisture. Okay, that's our first step. Next, we're going to calculate the free strain in each layer. This is evaluating how much do these want to strain due to the change in temperature and due to the change in moisture. We can do that like this, which we saw can be written this way. Okay, that means we're doing this calculation for every layer. So once again, that if we have 5 lamina in our laminate, we're going to do this 5 times. We'll have a set of free strains for each and every layer. When we're doing this on our paper, evaluating this, That means we have to carefully do these calculations and carefully document them so we can find the values when we use them a little later in the analysis. Okay. This free strain, once again, is how much each lamina, each layer, wants to strain due to the induced temperature and moisture effects. Now, if those are unconnected to each other, then that is exactly how much they will strain. But if they're attached together, then this is not how much they will be allowed to strain. That's irrelevant at this point because this is just the free strain. It's how much it wants to strain. And we need that to do our analysis. Okay, next we're going to compute the fictitious running loads and moments due to these free strains. That just means that we're going to take, remember the free strains, we have a set for every ply. So if you have a 5-ply laminate, we've got 5 sets of 3 strains. What we do is we take those strains and we pre-multiply by the Q bar. If we take the Q bar of ply 1, multiply by those free strains, which we called epsilon F, or we could just say it's the alpha delta T, right? So we've got the alpha delta T, we've got the beta delta C. If we take each ply and pre-multiply by the Q bar times that thermal strain times the thickness, that will give us the running load due to the thermal. For ply 1. We do the same thing for ply 2, ply 3, 4, 5, and then we add those all together, like shoving all those matrices together. That's the total running load due to thermal. We do the same thing for moisture, the moisture change, the same thing for the thermal moment and the moisture moment. So we're going to do that once for every ply and add all those up. We can write it this way. That the total hydrothermal running loads and moments minus or equal to the summation of the Q bar times the free strains times the thickness. What this means is we take the Q bar matrix for ply 1, multiply by the free strains for ply 1 times the thickness of ply 1. Then we add that to the same set of values for ply 2 plus the same set of values for ply 3 plus the same set of values for ply 4, plus the same set of values for ply 5. That is our total running hydrothermal fictitious running loads. We do the same thing for the moment by taking the Q bar of every ply times the free strains times the T Z bar. Add all those up together. Now we've got the hydrothermal running loads and moments. When we're all done, now we had 5, or as many plies as we have, times we have those for each of these in each of these stacks. But when we're all done, we've got 6 values. We've got 3 running loads and 3 running moments. These are fictitious running loads and moments due to the total effect of the temperature change and the moisture change. Got it? And stay tuned. Here we go. Now what we're going to do, we can say this is the total load that it would take to make the laminate strain in exactly the way that the temperature and moisture demand. This is the total strain that it would take to make the laminate strain the way temperature and moisture demand. It was developed by taking the free strain, what each ply wanted to do, and adding up all the effects of those. And now we have the running loads and moments that will have that same effect. Now once again, each ply, the first ply is not going to be able to strain the way it wanted to. But we took how much it wanted to calculate its contribution to the running loads and moments. And we did the same thing for every ply. To find out what it actually does, we have to do a little more work. So stay tuned. Now we're ready to calculate the hygro-thermal and residual strains. Okay? So if we take our fictitious hygro-thermal running loads and moments and we pre-multiply by the inverse of the ABBD matrix, we're going to end up getting the mid-plane laminate hygro-thermal strains and curvatures. So we've got the ABBD matrix. We're taking the inverse of that. We're multiplying by the hydrothermal running loads and moments. That's 6 values, 3 and 3. And that's going to give us 6 values of strain. 3 midplane strains and 3 midplane curvatures at the midplane of the laminate. Got it? Okay. These are called the residual, these are the hydrothermal strains. These are the strains at the midplane due to those hydrothermal effects. Okay? This is the real strain that occurs. Remember, we looked at each ply and what it wanted to strain, add up all the effects of that, use those virtual running loads and moments, and now have calculated how much this laminate really strains at the midplane, how much it strains and bends, the strains and curvatures. Okay. That's called the hydrothermal strain. Now, we can now use those midplane, the middle of the laminate values, to calculate the actual strains in each and every lamina, each and every ply. So now we take those 3 and 3 values, and we're going to use those for each of our plies. If we have 5 plies, we're going to do 5 more calculations where we're going to take the midplane strains and add them to the Z-bar times the curvatures. Okay? Now, this shows here in our slide, it shows Z, because we can use this to calculate the strain anywhere. But what we're going to insert here is the Z-bar of every laminate, that midplane value, the Z-bar. Z-bar times the curvatures plus the midplane strains of the laminate will give us the strains in each ply. So if we put in the Z-bar position of ply 1, we're going to end up getting out the hydrothermal strain in ply 1. If we put in the Z-bar position of ply 2, we're going to get the hydrothermal strain in ply 2, and so on. So we do this once for every ply. We now have, however many plies we have, number of 3 values each for strain. Okay, this is the hydrothermal strain. This is the total strain in body coordinates of the kth lamina due to hydrothermal effects. Now, if we want to know how much strain causes stress, we're going to have to remove the free strains from this. So when we call this hydrothermal strain, what we're saying is this is the strain that occurred due to hydro and thermal effects. But it also includes the free strain that thing wanted to do. Remember, the free strain causes no stress. So now we're going to remove the free strain. So now we have, for every ply, we have a set of strains at the midplane of that ply. And now what we're going to do is go back to our earlier calculation. We're going to grab the free strains for the same ply. So when we look at ply 1, we're going to take these hydrothermal strains. We're going to subtract its free strains that we calculated earlier. And that's going to give us 3 residual strains, which is the strain that actually causes stress. It's only a portion of the total strain on the lamina, but it's the part that induces stress. We're going to do this calculation for every ply. So now we have, if we have 5 plies, we're going to have 5 sets of residual strains. Okay? We can actually, once we have those body coordinate strains, residual strains, we can find the principal material direction strains in every ply by pre-multiplying by the T matrix of that ply. Actually, there should be a subscript on this T, right? Because what we're going to do is take the residual strains and body coordinates for every ply, and we're going to pre-multiply by the T of that ply to get the residual strains in principal material directions. Remember, while we need to do work in our body coordinate system, the only place we can evaluate failures where we have allowables, and that will be in the material principal direction. So we need to transform these into the 1 and 2 and 1, 2 directions so we can evaluate the strains and stresses. We do this for every ply. This is the residual strain and material principal coordinates for the kth laminate due to the hydrothermal effects after removing our non-stress causing strain. We're now ready to calculate the stresses that actually occur in the lamina. We call these residual stresses. Another name for these residual stresses and strains is mechanical strains. Some books call these the mechanical strains. I actually don't like that word. I like the residual stress and strain better term. Okay, so now what we can do, now that we know the strain, the residual strains and principal material directions for each and every ply, we can take each and every ply's residual strains and pre-multiply by that ply's Q matrix in order to get our stresses in the principal material directions. As we see here, we could have actually jumped ahead from our body coordinate strains and turned that into the body coordinate stresses, residual stresses, by just pre-multiplying by the Q bar matrix. That works too. And that avoids that transformation of the strains that requires the Reuter's matrix to account for it. So when we're all done, we end up with principal material stresses. Now, those principal material stresses actually, we're now ready to evaluate the strength of the laminate. We would take the stress 1, the stress 2, and the shear stress, and we look at each and every ply, and we compare those to the allowables for that ply. So if we're using a max stress kind of approach, we just write a margin of safety on sigma 1 against its allowable, sigma 2 against its allowable, and tau 1, 2 against its allowable. If you're using one of the failure theories like the Cy-Hill or the Hoffman, then you would take all three of those values and plug into your failure criteria. Now all this assumes that you know what the allowables are. We do have allowables for those materials, but we mostly have room temperature allowables. A lot of times, if you have at elevated temperature, most composite materials will have a reduction in allowable. Sometimes if you reduce the temperature, they'll have an increase in allowable. And same thing for moisture. Moisture tends to reduce the allowable as it increases in the lamina, in each lamina. So you may need to go out and do testing to get your temperature and moisture allowables at the levels of moisture concentration and temperature values that you're seeing. But assuming you have that, you can do that now that we know what the principal material stresses are. Okay? When we're all done, these are the actual residual stresses and material principal and body coordinates due to hydrothermal effects. Now, once again, if these lamina had not been attached, they would have done their free strain and we would have been done. No stress. Because they are attached together, we had to go through this whole process to find out how much of the strain that occurred actually causes stress. We found out it wanted to strain a certain way and it couldn't. So it strained a different way. And part of that different way's stress caused stress. And part of that didn't. And that's what this accounts for. This is how we go through the process to calculate stresses in material principal coordinates for a composite laminate subjected to moisture and thermal effects. Now let's see how we can do this process if we have external loads as well. That's going to be on the next slide, so stay tuned. All right, I'm going to lay out the whole process, so a lot of this is going to be a repeat of what we just did. Remember, we have a temperature change and potentially a moisture change. We calculate it like this. We're going to need to go get our global coefficients of moisture and thermal expansion. We calculate this in the same manner as before. We calculate our free strains for each lamina like this, as we did before. Said that. We're going to calculate the fictitious running loads and moments due to the free strains in the same manner as we did before. You got that? Now, so far, all of this is identical to what we did on the last slide. because in the last slide we dealt with moisture and temperature. And now we're going to do the same thing, but we're also going to introduce external loads, so stay tuned. We're now going to calculate our hydrothermal strains just like we did before, and we're going to calculate the strains due to the external load. So here's where the first piece that's different than our last slide. We went all the way up to these hydrothermal strains before, but now our next step is to compute the strains due to the external loading, which we can write this way, okay? This is the strain that the laminate midplane due to external load. Okay. Now, if we want to compute the total strain at the laminate midplane due to all effects, we can write it this way. The strain due to external load plus the strain due to hydrothermal effects. Once again, we're dealing with the midplane of the laminate, so we have strains and curvatures for the external load and strains and curvatures due to the hydrothermal load. And we're going to call the combined strains and curvatures EHT as our superscript to show that it has external load and hydro loads and thermal loads. Okay? Therefore, the total strain at the midplane of each level based on these loads can be calculated this way. We're going to take those midplane strains and curvatures, and this gives us the strain in each ply due to the combination. We're going to compute the strain that causes stress, which is called the residual value, right? In this way. And now we're going to give this the superscript ER, because it's the residual still, but it includes external loading as well. So the total strain, including both, is the EHT minus the free strains. Once again, this is done on a ply-by-ply basis. We can compute these, turn these into principal material direction strains, which can be converted to principal material direction stresses. And this allows us to estimate the stresses due to a combination of temperature and moisture and external loads. Got it? All right. So there you have it. We now can take moisture changes, temperature changes, and external loads. We can take any one of these, or all of these, or any combination of these. And we can evaluate our composite laminate to calculate the midplane stresses in each and every ply, so that we can evaluate whether our composite laminate will fail or not. This is an important methodology that is useful for composite analysis. Hope you enjoyed it. If you want to benefit from more of this kind of content as I keep adding clarity and ideas and example problems, be sure to subscribe. Also, I'm going to encourage you to leave a little note. If you like something, to talk about that on the video. If you have a comment or a suggestion or some other thing that you've learned, trick of analysis, feel free to drop that in the comments on the video and I will do my best to respond. Enjoy.